Hello everyone. In this lecture, we will focus on finding the relation between the location of the poles of the system and the step response parameters. So for a second order system, in the general form, the poles will be located at minus zeta omega n plus minus j omega n times the square root of 1 minus zeta squared. So we will have two poles, 1 and 2, located at these positions. You can see that the real part is equal to minus zeta omega n, and the imaginary part is equal to omega n times the square root of 1 minus zeta squared. We call that real part zeta minus zeta omega n that we have, we call it as minus sigma d plus minus j times, instead of omega n times the square root of 1 minus zeta squared, we can also use the omega d. The omega d is called the damped natural frequency. So we can say that the poles of the system, of the second order system, are located at minus sigma d plus minus j omega d. For the underdamped systems, they will be located in the S-plane in the form of complex conjugate poles. The real value will be equal to minus zeta omega n, and the imaginary values will be equal to plus minus j omega d. Then if we find the distance of any of the poles from the origin, so this distance, it will be equal to omega n. We can use the simple rule that we have. If I call it a squared will be equal to this distance squared, which is zeta omega n squared, plus this distance squared, which is equal to omega n times the square root of 1 minus zeta squared squared. So we will get zeta squared omega n squared plus omega n squared times 1 minus zeta squared. And then we will get zeta squared omega n squared plus omega n squared plus zeta squared omega n squared, and this will give us a minus zeta squared omega n squared, and this will give us omega n squared, and therefore a will be equal to omega n. Alright, so that distance will be equal to omega n, and then if we consider the angle that we have here and call it theta, cosine of theta will be equal to zeta. Okay, so this is important to remember. Cosine of theta, which could be obtained as zeta omega n over omega n, will be equal to zeta, and the distance itself is equal to omega n. Now we will see how the step response parameters and the location of the poles are related to each other. If we first consider the overshoot, or MP percent overshoot, we know that it is related only to the zeta. And if you remember, as the zeta decreases, overshoot increases, and vice versa. And on the other hand, we know that zeta is equal to cosine of theta. So if we have two systems which have the same angle theta as each other, they will have the same value for zeta, and as a result, the overshoot that we get for those systems will be also the same. Okay, so if let me draw it here. So if you assume that we have two systems with the same theta, let's say one has the poles over here and the other one has the poles there, both of them have the same theta. So theta 1, let's say, is equal to theta 2. Both of the systems have the same value for theta, and as a result, zeta 1 is equal to zeta 2, and therefore mp1 is equal to mp2. Okay, so if you have two systems, two second order systems, which have the same value for zeta, or they have the same value for this angle theta, they will have the same overshoot. And you can see it here. So if I have systems with the poles on this, let's say, line, all of them will have the same overshoot. Or if I have systems with the poles on this line, all of them will have the same overshoot. The next step response parameter to consider is the TP, or the peak time. We know that it's equal to pi over omega n times the square root of 1 minus zeta squared, or it's equal to pi over omega d. So we can see that TP depends on the value of omega d. If we have two systems with the same value for omega d, they will have the same peak time. On the other hand, we know that omega d is the imaginary value that we have for the poles. So our poles are located at minus sigma d plus minus j omega d. And it means that if we have two systems which have the same value in terms of omega d, if this is system number 1 and this is system number 2, since both of them have the same value for omega d, it means that both of them will have the same peak time. You can also see it over here on this graph. So if we have systems which have the poles on this line, on this horizontal line, which is parallel to the real axis, then those systems will have the same value for the peak time. And we can also discuss about the settling time. We know that settling time depends on the value of zeta omega n. So if we have systems with the same value for zeta omega n, those systems will have the same settling times. And zeta omega n is the real part of the pole indeed. Yeah, you can see it over here. So if we have two systems which have the same value for the real part of the poles, if you have one system with the poles here and the second system with the poles here, then for both of those systems, the value for the settling time, either 2% or 5%, those values will be the same because they have the same value for zeta omega n. And in terms of the rise time, since we know that the rise time for the system is equal, it could be approximated indeed in the form of 1.8 over omega n. Therefore, if we have systems with the same value for omega n, they will have a similar value for the rise time. And we also know that the omega n is the distance of the pole from the origin. So if I have, let me maybe draw it here. If we have two systems, I try to draw a circle here. Not a precise one, but still it should be okay. So if you have two systems with poles here and there, since their omega n is the same, the rise time that we have for them will be also similar. Here you can again see that if we have three systems, 1, 2, and 3, in the first case they have the same zeta omega n. Therefore, the settling time will be the same for all those three systems. In the second graph, we see that their omega d is the same. Therefore, the TP is the same for both systems. You can see it over here. In the third case, the theta is the same for the three systems, and it means that zeta is the same for three systems, and as zeta is the same, MP or percent overshoot for all three systems will be the same. And you can see it over here. Okay, I didn't draw it properly, but if I do it, you will see that all these three systems have the same overshoot. You can also compare the systems in terms of determining which one has a bigger TP or bigger overshoot. For example, in the third case, we see that all the three systems have the same MP, okay? But they have different values in terms of TP. So we see that for system number 1, TP is the biggest. Then we have it for TP2, and for the third system, it is the smallest one. We know that TP depends on the value of omega d. You can see that omega d1 is smaller than omega d2, and it is smaller than omega d3. And since TP is proportional with 1 over omega d, out of here we can determine that TP1 will be bigger than TP2 and it will be bigger than TP3. Okay? Or we can comment on the settling time value over here. We can see that zeta omega n1 is here, zeta omega n2, and zeta omega n3 is there. Or in other terms, zeta omega n1 is smaller than zeta omega n2, and it is smaller than zeta omega n3. And since for the settling time we know that it is the settling time is proportional to 1 over zeta omega n, we can say that TS settling time either 2% or 5% for the first system will be bigger than settling time for the second, and it will be bigger than settling time for the third system. Well, it is kind of shown here. You can see that for the third system, the settling time should be somewhere maybe around here. For the second system, somewhere around here, and for the third system, somewhere over here. And you can do all kind of comparisons in terms of the step response parameters by looking at the location of the pose of the system only. Okay, so if you have two systems with the location of the pose which are different than each other, you can comment on the step response parameters in terms of which parameter for which system is bigger than the other one. Here we have two examples. For the first example, we have a system where the values for omega d, zeta omega n are given. So omega d is equal to 7 and zeta omega n is equal to 3. And we want to find out the value for zeta omega n, TP, MP, and settling time. We can find the value of theta. We know that zeta is equal to cosine of theta. We have the values for, so here we have 3, we have 7. We can find out the value over here, or omega n. Omega n will be equal to square root of 3 squared plus 7 squared, which is equal to 9 plus 49, and it's equal to square root of 58. Once we have the value for omega n, we can find out the value for zeta. So we will have omega n, and then zeta will be given, and afterwards we just plug these values into the expressions that we have for TP MP and settling time, and you get the numerical values. For the second example, we have the system, mass spring damper system in the rotational form. We have the parameters given for J and D, so we don't have the values. For K, we have the value provided. And then we want to figure out what values should we determine for J and D in order to yield 20% overshoot and the settling time to 2% of 2 seconds. So MP needs to be equal to 20% and 2% settling time should be equal to 2 seconds for a step input of the torque. So what we need to do is to determine, first of all, the second order system's expression, so omega n squared over s squared plus 2 zeta omega n s plus omega n squared. We need to find out the transfer function for this system, and then out of that we will get expressions for omega n and zeta, okay, in terms of J and D. So these will be functions in terms of J and D, and out of here we will get values for zeta and omega n. Comparing what we have over there with what we have here, we will get the values for J and D. Okay, so I think it's kind of straightforward. You just need to determine the transfer function for this system. Once you have the transfer function for the system, you just follow these steps and then you will end up with the values for J and D that we want to have in order to satisfy this 20% overshoot and 2 seconds settling time requirements. Alright, so that's all for this lecture. Thank you for watching again.